take again good morning and good afternoon, everybody. Welcome to the Global Lecture Hall for yet another cool lecture of a Shanghai lecture series. Today we will continue with the main thread. I will continue in a few minutes with let's say main thread of the lectures, and then we will have two guest lectures, one from Professor Calla from Palermo on machine consciousness, and another one by Christopher Lueg on the informational, in the sense of information theory implication of embodiment for the behavior of intelligent agents. So welcome everybody. I know that the students have started to do some activity on the koans. I really hope this is an opportunity to go deeper into the issues of natural and artificial AI. So we just let's take the discussion. So we have seen that actually the idea of building intelligent agents or agents able to simulate the behavior of a living or of an intelligent system are quite old. Actually, this example from the Jacques Droz brothers is not the older one. There are examples going back to 5,000 years ago in China. And there are many examples in Greece, there are examples in Japan. This is more or less an example, Japanese example of the same age. We also have observed that what actually happens is that the design paradigm of most robot systems that are currently developed is not that far in principle from the idea of those ancient automatons, because what we have is state machines which govern a physical, a mechanical system. Now this is true for this example from the golden century in Spain, at the times of Charles V, the Emperor Charles V, and for more recent androids. So it's and then this is something that we should never forget. We have seen that we are already seeing a dramatic kind of explosion, for sure. A dramatic increase in the application of robotics, based actually on this that we may dub as a good old-fashioned paradigm. So, and then this is a picture that I have shown previously. This is I would say, our view on how things will develop, have developed so far, and how are they going to develop in the next decades in the area of robotics and AI. So we are now in the second wave, according to this picture. So where after we are starting to implement into these robots that we see around us, we are implementing machine learning techniques. We are really starting to use AI in robotics. And we are trying to exploit the possibilities given by the Internet of Things. So having a sensor under a chair makes it extremely easy to understand if someone is sitting there. And then, the idea is that there are limits in this approach, and that at some point it will become difficult to implement really autonomous behaviors which allow the robots to interact fluently, adapt to an open-ended environment where strange things happen all the time. No? So, and the consideration that we did was that if you look at, because the lecture are about natural and artificial intelligence. No? So on the one hand, we want to see how AI is making progress, and where AI is artificial intelligence. So it's the design of artificial agents showing an intelligent behavior. On the other hand, we are also interested in reverse engineer natural intelligence. So we really want to understand what are the principles underlying the behavior, I would not say of a human brain, but mind, but even of apparently stupid animals like spiders or other insects, which in many cases show much more adaptive and to the environment, to a real-world environment than current robots. The observation that we did is that living systems are actually operating on a different blueprint. So, because on one hand we have this top-down control paradigm, which also in extremely successful cases like the Asimov can actually show what I never stopped to underline, that is the show poor reaction to unexpected events. On the other hand, we have this bottom-up, self-organizing systems based on many agents interacting stochastically. So the idea is to understand to what extent. So the challenge that we have is to understand to what extent we really. So this is a biased point of view, no? But to what extent we really need to implement those principles that we see in nature into artificial agents to have the kind of behaviors that we want. And there is another, on the scientific side, and we are going to have actually the first of the two guest lectures today will be on this topic. We still have serious problems to understand what we mean when we mean that we are conscious from a scientific standpoint. No? So we see that our intelligent agents are not so intelligent, and also we see that we from a scientific standpoint we have problems, and Antonio will give us a lot much better insight on this to understand what does it mean to what really means in terms of system property, the fact that the system knows that it is there, he or she or it is there. No? So I don't know why I know that I am here and you know that you are there in terms of properties, minimum properties that the system needs to have. So and then we have this more weird concept like that of plant intelligence. Now, plant intelligence seems a strange idea, but if you check, if you have time to check, or you wish to check last year's presentation by Barbara Mazzolai in the Shanghai lectures, you will see that to a certain extent, if you consider not our time frame, which is actually in the seconds or the minutes or the hours, because we react in a matter of hours, but if you consider the years or the days, the months, the years or the centuries, actually the capabilities of plants to adapt to the environment are remarkable, and they are interesting because they have no brain, so they are absolutely a kind of alien intelligence very close to us and mostly neglected. But again, the point is that what I really mean when I say intelligence, and this is the main thread of all the lecture. The idea is that we should chase, and this is a quite, so it's biased, it's a point of view, the idea of a cognition as an emergent process from sensory motor and integration processes, interaction process. And in terms of, actually, we expected a student presentation on the frame of reference today. The frame of reference is actually the problem which affects the purely symbolic approach. No? Because if you look, if you remember this example of Simon Ants on the beach, if I change by 100 times or 1,000 times the dimension of the ant on this same beach, the behavior change completely. So all this apparently intentional behavior of the ant, which avoid rocks, moves into the valley and climb the hills of the beach, is actually changing completely if the ant is much bigger, so it don't even notice the hills and the valleys and the rocks, which now are small stones, not the valley. So, and then the problem just to that affects. So while the frame of reference problem actually affect what we very broadly we can define the symbolic approach. The sensory motor approach, so emergentist sensory approach is based on sensory motor interaction. So the idea that the proper behavior emerges from the sensory motor interaction, like in the case of the hand, no? So actually the interaction with the real environment, the real agents, is what actually creates, go immediately into another problem, which is the problem of a symbol grounding. So how, finally the symbol representation of reality emerge from this sensory motor interaction. No? And now, last time I was taking the opportunity of the fact that we had a surprise connection problem in one of the guest lecturer. I introduced this idea of surprises. No? So I introduced to you this idea of surprises, no? Because essentially when I say that the system needs to be able to adapt to unexpected event, I want to say that this system should be able to deal with something that the system didn't expect. So if in case I want to give a measure of the capability of a system, now because this is typical scientification, so because I say, and then clearly an ant is much more adaptive than any robot that has been built so far. This is a very strong statement that I should be able to prove, and to a certain extent it is a qualitative statement based on intuition. Right? So if I really want to justify a statement like this, I should be able to say what I mean as an unexpected event, and then to check if a system is able to which kind of events a system is able to manage, because actually it's not true that Asimov is not able to manage unexpected event. In 2008, when that famous Asimov false video was recorded, it wasn't able to detect a small disalignment of a stair. Now it is able to manage that, but for sure there are other unexpected events. The point, if you check it in the textbook, the example of a Dennett robot try to dispose explosive, the idea is that in principle I can add more and more management, more and more routines, functions managing the unexpected events that with time I discover are relevant for the life of my robot. This is not impossible to do. Of course, if I have a system which is able to manage to create by itself the proper behavior, the process is made easier. Also, if you think to example like remote place exploration, deep sea or space, it might be difficult at design time to understand what to list all the cases, no? Because the problem with not having an emerging self-organizing process, a set of processes, is that I need to know in advance what's going to happen. So just the idea is that I may have various kind of distribution. Think to a normal distribution, and then a surprise is when I find something which doesn't comply with the expected distribution. Then in these slides, what you see is a list of the kind of distribution that you can at first glance think of if you are more or less a scholar or a student. Of course, they are dependent on the kind of modeling that we are developing. A nice idea that was actually published recently, last year, in Nature, is the idea of the adjacent possible. No? Because what is the adjacent possible? The idea is that in what really we observe in nature, we observe in our experience, is that sometimes when there are certain kind of key changes which enable a burst, a sudden explosion of many more changes. This can be modeled, and a model can be found in this 3 studies in Nature 2014. But what I want to say is that also problems that you may think are far from the issue of from science about what's the nature of intelligence and what's the nature of consciousness, like innovation. What's innovation in business is again related to this, because what we actually see is that this model proposed by TRIA of the adjacent possible actually works into the economical sphere, no? Because we see the introduction of a microprocessor and suddenly we have a lot of innovation. Then you have the internet and this carries a lot of new innovation. Any new, there are advances which actually trigger a snowball of more advances. And this happens into the economical sphere and as well as it happens in nature. So we are not actually considering very different things. Now, I don't know, talking about how to simulate, for example, attentional processes, now because we are trying to reverse engineer what we mean as intelligence. So an example is this video with the ICAB and the blue ball that I think Nathan has on the if you look at this now, it seems very natural. No? So it seems that I can behave almost like a baby. No. So the question might be: so what's the difference? And to a certain extent, so it's not so trivial to say why a system behaving like a conscious, not even intelligent, but a conscious being is not actually conscious. No? I think we all agree that the archetype is not a self-conscious being. But if you things are programmed, we are sensitive to certain cues. No? Certain ways of showing, moving the eyes, a certain way of reacting to, for example, a blue ball, we are easily led to attribute some kind of intentional behavior to a system like this. Actually, you may remember from the I think first or second lecture by Rolf that even if you look at a movie of triangles and squares moving almost randomly on a 2D surface, you are instinctively led to attribute behaviors like, so the triangle is chasing the square. No? While obviously it's not happening. So this is another issue. So the fact that we study in intelligent behaviors, but we are definitely biased. So if I attribute to some of you the fact that you are conscious, I'm probably right. Even when I mean probably because you may imagine the weird. So some of you might be a very advanced robot that behaves like a student, right? Instead of students behaving like a robot. But this is I'm right because statistically, you're evolutionary. We have co-evolved, and so I know that you are like me. But if you think about it, I don't have a very strong argument. Huh? So and then I don't really want to enter into this topic, but I leave to the first of our guest lecturers. So there is a lot of activity in this area. No? So people trying to understand what does it mean to so because the problem again is what are the system properties, that minimum system property that the system needs to be alive. What are the minimum system properties that the system needs to be intelligent? What are the minimum system properties that the system needs to be conscious? And then, is there an overlap? So I need to be, to a certain extent, alive to be intelligent, or it is not needed? I need to be, to a certain extent, conscious to be intelligent, and to be conscious, I need to be, to a certain extent, alive, and to a certain extent, intelligent. And in which sense? Those are all mostly open issues. And if some of the things from this emergentist standpoint, so this idea of embodied emergent AI, some promising idea have been proposed by Damasio and Tononi, who essentially frame the problem in terms of integration. So, for example, my favorite model is Tononi's model, where essentially a system to be conscious needs to have a minimum level, so a certain, let's say, big capacity of managing information, and then needed to be able to synchronize these different information-rich activities. Might be more necessary condition than a necessary and sufficient condition. So probably you at least need to have some capabilities in terms of managing information and to integrate information in a different area of this self-organized multi-process system. But probably there might be something more. And then you may remember, you may check the guest lecture by Kevin O'Regan a couple of years ago, who actually claims that this is a false problem, and what you should really look at is the interaction. No? So again, on the topic of unexpected events. No? So you can expect Gaussian behaviors, you can expect power law behaviors. So in general, you can draw whatever line or as a probability distribution of your events on the screen, and then you can see if what happens is in respect that expected behavior, while in general you will be so, and then you have so again on this topic, so should cognition, to what extent cognition is related to life? So as my system to be to a certain extent alive, to be able to behave properly in an environment. This is an open issue. No? So I would say yes, but of course we don't have. Of course we still don't have many proofs. So an interesting idea. So it's an interesting idea has been proposed by Chaiting recently, which actually is not completely. So there are several ideas. Now, an idea which, by the way, taken by Stuart Kaufman and others is that the autopoietic idea. So the layering system is a single system which self-reproduces itself. So it's able to reconstitute itself, produce itself, basically. Autopoiesis in Greek. And actually, from the original way of thinking of Maturana and Varela, which is more or less taken by Kaufman, this autopoiesis is equal to life, and life is equal to cognition. Then there is another approach, which is kind of this is a kind of thermodynamic approach. So life is a kind of reverse thermodynamic process. Then you may have a different approach, like Chaiting's approach, which was proposed recently, where he essentially say that life is about information, is about writing programs, natural emergence of program, and what essentially is life is a kind of random walk in the program space. Now, so you may think of a program which is made of statements, like in evolutionary programming. So you have a series of statements that evolve naturally. But naturally, what does it mean? That the statements are changed at random, by chance, and so your program, in some way, is doing a walk in the world of a possible space. This is, I think, is a very nice idea. The limit is that so what I should consider is that those programs are also embodied. So this is part of my program, and this is pure dynamics is my body. So how to connect these two things together is an open issue. Just to go back to a textbook, this example is the example in the block world of it's again the Dennett's example. No? But I don't want to. The idea. So the idea is twofold, because on one side, I'd like to get rid of the complexity of writing a very long million of line of codes program to do what I want. On the other side, organizing a system which is able to evolve the behaviors that I wish when interacting with the external environment is not. So it's actually a research issue. If you remember the three waves picture that I like to show every time, why the third wave is not now and we are in the second wave? Because to have a third wave where we exploit emergent processes, morphological computation, and so on and so forth, we need to understand something that we are researching now, so that we understand to not completely at the moment. So. So this, I don't want to spoil the students' promising presentation of a frame or of reference, but if you got it, the problem is that this frame of reference is what drives my design. So when I program a red, a blue ball for my robot, it's that I already know that there exists a blue ball, which has a meaning in my frame of reference, but not necessarily is an object in the frame of reference of my artificial robot. If you allow me to quote Philip K. Dick, so the title, you may know that the novel from which the Blade Runner movie was taken was Do Electric Ships, so what do electric ships dream? So a system which evolves its own emergent behavior and representation of an environment may represent the environment in a different way. So a key point is if we believe that cognition emerges from interaction. A key point is the fact that we have to talk, we cannot discuss, remember the functionalist hypothesis. So you may think that you have abstract intelligent behaviors which can actually operate in a computer completely disconnected from any kind of environment. And this is probably less likely by people operating in robotics who actually always have the physical system operating, exerting or receiving forces into a physical, well-defined environment. So you have to. So if you put yourself from an embodied standpoint, you need to think about the complete agent. So you need to design the full agent before starting to talk about behaviors. Because another point is that I really want to define intelligence, and we have seen that there are plenty of different definitions of intelligence. Or I am more practical and low-level objectives like studying when certain behaviors that I want to see in my agents occur. Or I want to understand under which condition a natural system can behave in a way or another way, without sticking too much to trying to define an abstract characteristics. Now, you may also remember all the discussion of the QI. So what does it measure QI, and why engineers and people in the science have usually higher IQ than people in the humanities. Does this mean anything in terms of intelligence? Maybe you would argue not much, but so this is this agent. So it's a concrete agent. This means that it will be subject to the law of physics. The sensory stimulation, so the flow of data which enter into the system, are actually not coming from interaction with a real world which behave according to the law of physics that we know. Then the system is able to act on the environment. No? So, for instance, if I look at this and I don't see the content, I can do this, and so I see what's inside this small bag. This is part, of course. Another point is that I've been decades doing this kind of operations. So it's not just my interaction here and now, but it's also the interaction that our species, in this specific case, had during the evolutionary process, and Verena talked about this, and also there is a developmental approach. It took me a lot of time. When I was 6 months old, I wasn't able to do these things with this dexterity, and this ticket for an exhibition that is here in this small bag had no meaning for me. It was a kind of so actually it's physics. It's the fact that I receive stimulation from a real environment. I react to this real environment, and a dimension that was not was already discussed in the previous lecture is time. So it took time for this system to evolve in order to be able to do this simple operation, and it took time to me, I mean really me, to learn to recognize those objects and to be able to do this kind of discussion. Then, for sure, all those systems are complex dynamical systems, meaning that we have, for instance, that we have many, in the trivial sense that we have many processes interacting, but also in the sense that we can have chaotic behaviors. So we may have small inputs giving big outputs, and the opposite. And we have a lot of probability of random events. And then, last but not least, part of a computation is embodied. So when I was talking about the idea of life as a random walk in the program space, and say, yes, very nice idea, but the program is embodied into the agent. Because if you think about the example of a corner ranger actually has no control. So, and essentially no computation, or a very limited computation, just giving a bit of impulse at every step. But essentially, if you think to the same corner ranger, not the corner ranger, but the typical MIT or Cornell passive walker going down the slope, in that case you have a zero computation and zero energy input, and you have a behavior that you feel is extremely natural. So, recap, so subject to the law of physics, sensory stimulation comes to a real physical environment. Environment is affected by the behavior of a system, and there is this interaction. So the interaction is what actually allows the agent to have a representation might not be liked by some more radical people believing in the emergentist paradigm, no? Because say representation, but the idea is that the representation could be, you may have two kinds of representation. Representation which is coded by me when I write the program governing the robot, or might be a kind of representation, so some kind of abstract structure that the system uses to behave into properly into the environment. In fact, we see, okay, there are two nice famous papers apparently in contradictory, because one is Intelligence Without Representation by Ronald Brooks in the 80s, and then there is Luke Steele's paper Intelligent with Representation, which is some 10 years ago. But the nice thing is that the point of view of Luke Steele is actually an evolution of so you may have some kind of representation that I call representation for simplicity, which actually is a compact representation, a compact mapping of the environment into the agent. No? But and by the way, I was talking about complex dynamical systems which also are non-linear. Does anybody want to give tell the difference between a non-linear and a linear system? Actually, I'm talking too much. I should stop more frequently. So a typical characteristic of a non-linear system with respect to a linear system. So, or if you want, what's typical of a linear system?
From Chile, I'm not completely sure, but I imagine that the difference between nonlinear system and linear system is similar to the nonlinear classifiers and linear classifiers. So basically the linear systems, I guess that with similar inputs are going to have similar outputs. So it's the response is linear, but in more complex or non-linear systems, even similar inputs may have quite different outputs, I guess.
Okay, yes, essentially this is the difference, and very appropriately you put it in the concept of classifier, no? Classifier actually do, so which are in the slide of the three waves are in the second wave, are typical machine learning tools, so a way to classify data in several categories, and exactly what was taught. So in a linear system, small inputs, if you have a superposition of effects. So if you choose small inputs, you will have a related sum of the outputs on the other side. With non-linear system, this is not granted. No? So you may have big differences in the input in the data, in the case of classifier, without having big changes in the classification, or the opposite. So, yeah, you may check page 93 of how the body shapes the way we think, and so there are a number of issues. No? The main I would say, negative characteristic of a nonlinear system is the limit of the predictability of the behaviors and the sensitivity to initial conditions. And then there is a potentially long list of design system that we will get into in the next in the next lectures. I just before stopping, I just give you an overview. So the first thing is that is not. You will see that I do a consideration before, which is that I'm listing a long series of principles. Those principles should be translated at some point in some modeling practice and in some design methodology. Some model and some. And here is where we are weaker. So a free constituency principle is that I need to consider, when I talk about intelligent agent, the agent itself, the environment, and the set of tasks that I want. The complete agent principle is what I was talking before. Then I would like to organize my intelligent system as a set of parallel and loosely coupled processes. I would like that this emergent, call it representation, emerges from the information structuring of sensory motor coordination. I would have the simplest possible system, so I don't want to have a fully actuated walker. I want, if possible, a bike walker. And we have seen that then I have problems to change speed and to take turns. So I need to develop a model for that. I need redundancy. So if I want that my system is robust with respect to the environment, I need to have different. So a trivial way is multisensory. I need to put together sound and vision, so I'm safer. If the room is dark, I still understand something from the sound spectrum. Then, of course, the system needs to have a value, so it needs to, but this is more from the engineering standpoint, and needs to be in a stable condition with the environment. So the system should not destroy the environment and should not be destroyed by the environment. Since it's already late, I would stop here. So we may have 10 minutes of, so we can start again at 10:10. Yeah, 10:10. 10 after 10 CET with the lecture on machine consciousness by Antonio Calla, from Professor Calla from Palermo. And that's all now. Thank you. If you have any question, maybe we can leave for later, because I took too much time. It seems that we will continue the discussion maybe offline, because it seems that our time has gone for this video conference slot. So thank you, everybody. Thank you for your great lecture. Thank you for attending, and see you next week. Bye bye.
Okay. Bye bye. That's intelligent. They cut us off. I love these systems.